Right. So we have got a power station, and at the power station they make power. The way they make power is through a turbine twisting a generator. The generator has got magnets and it's got coils of copper wire, and it produces electricity at around 25,000 volts. For us to transmit electricity, we need those big tower things, those big electricity tower things. And those big electricity tower things have got wires in them. Those wires are thick, they've got low resistance, and we transfer the electricity at about 300,000 volts. Now that's too high for us to use in our homes. So for domestic supply, we've got to take it down to 230 volts. For us to turn 25,000 volts into 300,000 volts, we need to have a special little box here called a step-up transformer. And for us to turn 300,000 volts to 230 volts, we need a little box here called a step-down transformer. The reason why we increase the voltage to 300,000 volts is because if we increase the voltage, we decrease the current. Decreasing the current reduces the amount of power that's lost, because the power transferred is P equals I squared times R. So we've got low resistance wires, so the resistance number is as low as possible. If we increase the voltage, we decrease the current, which decreases the amount of power that's lost by heat through the wires. That means that we're going to save more money. We don't have to spend as much money on fossil fuels. A transformer is actually a very simple piece of equipment. It is an iron core. This iron core is laminated. You don't need to know about why it's laminated. You just need to know that it is. So we've got my iron core. The iron core is shaped like a square because we've got a primary side and we've got a secondary side. And the primary side will be connected to a source of power. It will be an alternating source of power. You'll have a wire and you'll have a certain number of loops. It's alternating current. It's AC current, which means that my electrons are flowing through the wire in one direction and then very quickly turning around and flowing in a different direction. Now in reality, the electrons are only moving a small bit, but it's the overall current that changes at a frequency of about 50 hertz. So about 50 times a second the electrons are changing their direction. Now, if I just got a battery and I connected that to a loop of wire. Hi, sir. Yes? Thank you. I'll be about 10 minutes, sir. If I've got a loop of wire and I put an iron nail through that loop of wire, suddenly I've made myself an electromagnet. Because remember, if I've got a wire with a current running through it, the direction that that current is going in will determine the shape of the electromagnetic field. Actually, I'll take them off. So if I've got current that's going through the wire in this direction, then the shape of the magnetic field will be this way. So it'll be towards me and back around again. If I've got current and it's going down that way, the shape of the magnetic field will be going into the board. So it'll be turning into the board. Can't tell the difference between those two wires, but hopefully you get what I mean. If the current's going that direction, the magnetic field is going this way. If the current's going that direction, the magnetic field is going this way. So if we change the direction of current, we change the direction of the magnetic field. If we have current going through my wire, then it produces a magnetic field. So here I've got current going through my wire, producing a magnetic field around my iron core, my electromagnet. If we see here, there's some current here, there's some voltage here, so we're going to have movement of electrons through my wire. It's alternating current, so it's changing direction. This is causing my iron core to become magnetized. So because there's current going through my wire, my iron core is becoming magnetized. The magnetic field is also changing. On the other side, we will have a loop with more coils, in this case, though not all the time, connected to a component. I now have a magnetic field moving through my iron core, changing directions and moving through a coil of wire. I've got a magnetic field moving through a coil of wire. If I was to have a very sensitive ammeter connected to a coil of wire, and if I was to have a magnet with a north pole and a south pole, and if I was to move this magnet through my coil of wire, forwards and backwards, I would see current being formed. A magnet moving through a coil of wire forms a current. Now, if I just put the magnet into the wire, there will be no current. If I don't move the magnet, there will be no current. And moving it forwards and backwards changes the direction of the current. So if I alternate the direction that my magnet is going, I alternate the direction of the current. In my transformer, I've got a source of current creating a magnetic field in my iron core, which is magnetizing the entire iron core, but because it's alternating current, it's also changing the direction of the current, which means I now have a magnetic field moving through this loop. This will produce a current, which will make my component work. It's called the generator effect. When I've got a current moving through a coil, I can generate electricity. Now, the important thing to look at here is the number of coils. I've got fewer coils here and greater coils here. We assume, for the sake of our exam, that this is 100% efficient, that my transformer is 100% efficient. So there's no wasted energy. Efficient. Here I've got less coils, here I've got more coils, which means the voltage here will increase when it's over here. I'm stepping up my voltage. This kind of transformer will be used to increase my voltage from 25,000 volts to 300,000 volts. I will have fewer coils on this side, and I will have more coils on this side. Swap that around, and we've got a step-down transformer. I will have fewer coils on this side, and I will have, more coils on this side, and I will have fewer coils on this side. It will change the voltage from being large to being small. Because we assume that a transformer is 100% efficient,